All right, yeah, please settle down. And so now we are moving to the big questions panel. And we have at least 2 or 3 troublemakers in the panel, so I think it should be lively. And the audience also, do not hold back. You know, this is the fun part, right, where we get to ask tough questions, ill-posed questions, and ping and prod them and see what comes out. All right, so the way the panel is going to work is, again, I'm not going to introduce everyone. Everyone's very distinguished, amazing CVs, but we'll save time. But you can see their affiliations on the screen here. So every member is going to spend maybe a couple of minutes, 2 or 3 minutes with opening remarks on anything that they think is relevant to the present discussion. And then I'll open it up to the audience, and then we'll go back and forth, okay? So we'll start with Petros, you want to start? Okay. All right, you want to collect your thoughts. All right, go ahead.
Morning, everyone. I'm Jonathan Carter. I'm the Associate Lab Director for Computing at Berkeley Lab. And if you've not been at a lab, an Associate Lab Director is a bit like a dean. So you might understand the nature of the remarks I'm going to make, given that. So like most scientific organizations, I guess, it's been remarkable to the extent at which LBL scientists across really broad domains have started adopting foundation models. And some of the problem characteristics I thought I'd just mention in my opening remarks are some things we haven't really maybe gone into so much so far in this conference, and that's foundation models as glue or grease, let's say. And what I mean by that is using them to connect together existing pieces of software to form toolkits, and just to make it easier to do things. For example, we have a high-performance computing center at LBL, and they've developed a chatbot, which basically a high-performance computer center user can use to interrogate the various help pages we have on that. And then a little bit more sophisticated is Jupyter AI plus the GPT Engineer plugin to give people hints about how to move application codes from desktops to architectures that involve, say, GPUs or distributed architectures. And in other cases, in kind of the glue cases, we've been using LLMs to transform data. In the area of building energy efficiency study, there are a lot of different data formats and software packages, and it's really helpful to be able to use a foundation model with some appropriate domain knowledge inserted in to be able to do these conversions rapidly and automatically. So those are just a few examples of us using foundation models in this way. And you might imagine as the models get more sophisticated, they could act as an interface, a kind of a scientific assistant for many other models, and also for driving experimental protocols or even traditional modeling and simulations. So I'm going to leave it there and pass the baton on.
Okay, yeah, I'll go next. Good. So we were posed a set of questions. Has the audience seen these questions?
In some form, yes. I've shown it a few times.
Yeah, so they were, I thought, wonderful questions, and I look forward to hearing what my colleagues have to say about them. But I wanted to actually sort of take a slightly different take on things and say that we don't know the answer to most of these questions, and we may not know them too soon. And we also perhaps don't even know if they're the right questions or if there are other questions we're missing. So as a very sort of applied, pragmatic person, I'd like to suggest that we should be thinking hard and talking about how we might address those meta questions, what are the important questions, by, okay. Shall I start again? No. By applying foundation models to challenging problems in science and engineering and seeing what works and what doesn't work. And doing that is going to require many changes to the way we work, I believe. So of course, we first of all need to probably build science-specific foundation models. We need to work out how to get those models into the hands of people. We need to work out how these foundation models are going to work in the real world of science, which is not typically people sitting and asking single questions, but engaging in interdisciplinary discourse, in using sophisticated instruments and computational methods. In other words, what we just heard from the previous speaker, working in situations in which glue is needed. So my two prejudices, I guess, we need to start working immediately on trying to solve hard problems. And secondly, we need to do so without agonizing too much about whether we're building artificial general intelligences or other superhuman capabilities, but thinking how can these models work as collaborators with humans.
Thank you. Payal?
Yeah, I'll take it right from there. So I think human-computer collaboration, human-AI collaboration is going to be it is already becoming very important, but so would the collaboration across different agents. And in my mind, like if we are talking about subjecting this agent to tackle scientific discovery or scientific workflow tasks, it should also have some of the self-learning mechanism over time and learn to control it in a more autonomous manner. So how few, all what it matters at the end, that how few interaction it can have with other agents or with other, or with other human investigator, and then from these few examples, if it can learn in a reliable manner in a more autonomous way.
It was on. Yeah.
That's very important. And as we build, these more powerful and general agents to handle such scientific challenges, the other aspect which naturally becomes very important is that how do we trust them and how do we have a governance mechanism around them? And I think that's what I also saw when I just had a glance at those questions, that what are some of the trust, what are some of the safety aspect of these agents. I think going forward, we need to have emphasis on both of them, because if we are really talking about allowing these agents to work on their own or work with some human supervision, but given that we don't have much understanding of the inner working of this mechanism, of this agents or model, how do we ensure that it is learning what I want it to learn and not learning something else? So I think all of this aspect of different way of ensuring and measuring and mitigating trust dimension and having a governance mechanism around that is going to be very important.
So the question that strikes me most is about how can we make these foundational models more creative and more knowledgeable. I think Payal also talked about that in her takeaway messages. So I have general thought is that I think we should start to let science guide AI rather than just to think about, okay, the AI technologies are good enough, we apply that for science. So more like science for AI. One thing we could do, for CS people, is that we probably need a better reading mechanism beyond transformers. The reason I'm talking about this is because, for one, we have so many multimodal, signals, right? When we read literature, we need to look into molecular structures, pathways, knowledge base, or things like, we normally don't care, like charts and figures in our transformer design. So it's more like multiple signals come in at the same time. So can we design a parallel reading mechanism? Just like how humans read papers, that you keep looking at external references and connecting dots. And related to that, when we read papers, we don't read it really sequentially, right? We read at maybe the experiment section first, method, and then we decide to read the intro or related work or not. So there's a natural existing hierarchy in this literature. So can we design a new reading mechanism so that we can compute the self-attention more efficiently and more effectively? Also, finally, I mentioned this a little bit in my talk. I feel that we need to enable these models to have a critical thinking capability before we apply this for inference or prediction or generation. So that means that the model needs to be able to fill in the blank, even if the knowledge is not explicitly written in the papers. So you need to be able to think of new ideas, connecting dots, and also maybe even do counter-argument hypothesis generation. I think some people here said that they are also doing like multi-agent debate. The good thing about these foundation models is that it can mimic multiple personalities and SPs, right? So before we apply these models to do any applications, we need to enable them to have their own like a research meeting, discussion, critical thinking, so that they can update their knowledge before they are applied for downstream applications. Yeah.
Great, thank you. Al, are you wearing your Michigan hat or NSF hat?
I'm wearing the challenged hat.
Yes, technologically challenged.
Okay, great. Yes, I am I'm Alfred Hero. I am currently at the National Science Foundation in the SCIES Directorate, Computing and Communication Foundations Division. I am also a faculty member here at the University of Michigan in EECS, Biomedical Engineering, Department of Statistics. So I'll be speaking at this panel with my Michigan hat, as opposed to trying to offer any strategic
You're on the other panel as well.
Advice from NSF. In my research, I am very interested in specifically in three of the questions that were put out here. One involves basically the ability to take advantage of infrastructure that will enable a true multi-agent instantiation of learning, which can benefit from both the great availability of data, but also from the various issues on privacy of that data, where some data may be private because it's perhaps intellectual property. It may be private because of HIPAA regulations. So it can't be shared. You can't gather it all in one place. So this really requires an infrastructure of let me say, federated learning, distributed learning, and privacy-aware protections for that learning. And so when you get into that discussion, of course, that brings up issues that go beyond what we currently incorporate into our training objective functions for single agent learning or multiple agent in one server cluster. Things like energy consumption, things like communication bandwidth, whether the internet has the required bandwidth in order to share information at the rates necessary in order to produce an expeditious result. And then computation too, the computational load, which could both involve the number of iterations in or epochs in SGD, or memory types of constraints. And so these are never really explicitly incorporated into the learning paradigm. And I think that's one area that is very promising through methods like coding computing, intelligent caching, and federated learning methods. The other thing I want to talk about briefly is the issue of new mathematical and statistical frameworks. I believe that the current trends, which are in machine learning, which are heavily based on the neuroscience emulation paradigm, is not the end all. That there are other paradigms that are worth considering. So we probably are all familiar with the debates among those that fall into the category of researchers that believe that learning is something that is acquired, is empirical, and that requires simply, a sufficiently large parameterization of a neural network in order to learn. So Yann LeCun, for example, is a big promoter of this, versus the point of view that learning requires some innate embodiment of human reasoning, syntax, semantics, and so forth, the Noam Chomsky type of approach. And we are currently, I think the technology is very well developed for the former, less so for the latter. More generally, I think that the paradigm of neuroscience is perhaps also somewhat limited, that if we go back to talking about multi-agent systems, there's a whole area of complex systems with dynamical, loosely coupled, swarms of computing, where emergence is much less understood than even when there's a single agent that we can take advantage of in developing models and predicting performance and improving performance of the current generation. And finally, let me point out that there are many other attractive mammalian systems that have the properties of learning, especially in adversarial environments. And I don't think we have to go that far to guess what the most exquisite system is, and that's the innate and adaptive immune system. And so part of my research over the past few years has been exploiting this distributed, intrinsically multi-agent system where instead of neurons, you have neutrophils, T cells, B cells of both circulating plasma type and also memory type that effectively instantiate a paradigm which actually can be traced back to a U of M faculty member who was not on your timeline, who was John Holland, genetic algorithm, which basically emulates the, this vast capability of a distributed system of literally billions of cells of different specializations to be able to protect against either disruptions by rare events or by forming antigens to pathological attacks, right, against the system. So let me stop there. I won't talk about the third area for lack of time.
Thank you very much. That was very thought-provoking. Yeah. Mike? So it usually takes...
I think it's on now.
Yeah, it takes 3 seconds.
So I'm glad Petra said start at the other end, so then I could hear what some people said. So I think these are all sort of important challenges, right? I mean, privacy and understanding some of the challenges Al was describing and so on. And at least for me, I have a hard time thinking about it, and I guess the reason is there's a couple sort of cultural clashes going on here, and people come at it in different ways. And at least in my experience, the answer you get is almost predetermined by how they come to the table and try and frame the question. So there's a thing called engineering, and there's civil engineering that sort of, to oversimplify, sits on top of physics, and maybe there's physical principles that underlie it. And there's software engineering, and those are very different. Software engineering, the abstraction doesn't need to sit on physical principles, right? There's design principles on good software abstractions. They may instantiate at a lower layer, and so those are sort of two very different ways to build or engineer systems. One's you're sitting on top of something physical and need to respect that in some way, and the other, basically, you don't. And then there's, if you want, so a lot of machine learning is engineering. Then we're talking about scientific machine learning, and science is a very different thing. It validates things. I mean, the way you get an induction in science is you ask falsifiable questions. It's not generalization theory in VC. You ask falsifiable questions. And, you never know you're right, but you can show you're wrong. I mean, the usual sort of thing. And so that is different than engineering in those two. And then there's theory to guide what's going on. And I think the word theory really means very different things in different areas. in physics and the sciences, theory has one job, and it's to compute numbers, basically, right? So physicists will cheat anywhere they can as long as they compute a number. They'll ignore sigma fields, invent Dirac function. I mean, they'll cheat anywhere they can as long as they can compute numbers. A lot of math doesn't do that. They want to prove a theorem. And a lot of the machine learning theory is governed by the latter. They want a theorem. They'll cheat on data, they'll cheat on whatever, as long as they get a theorem. Now they need to justify it some way, and so the way they justify it is to say, I have data in, data out, and I want to drive training error to 0, whatever. So what's going on inside the black box doesn't matter, right? So the word theory is very different there. And so I think, at least I have a hard time understanding how what the word intelligence means, or general intelligence, and these memorization. Memorization meant something very different in our BMs in the 80s than it did in the last 10 years. And so I think what I would say is there's one thing, I mean, if you're doing engineering, are you doing civil engineering or software engineering? Are you doing engineering that sits on top of something physical or not? And how you will want to ask questions will be different in those two cases. If you're using theory to guide you, are you using theory where basically the job of the theory is to make predictions? It's to generate numbers whereby you can ask falsifiable questions, or is the job of the theory to be normative? This is the way you should do it. I mean, there's value in saying SGD, even if there's a profound disconnect between the theory and how the methods actually work, to say, I'm going to do this because this is the way you should design things. And then, of course, how you should design it depends on whether you're in industry or at DOE or whatever, so that's usually not described. But I think if it'll be much easier to have a debate about, are you doing it on AWS and Google or DOE or GPUs and this and that, if you force yourself to ask falsifiable questions and are just very clear about whether you're using theory to do something predictive or something normative. And so until that's clear, I have a hard time reasoning about a lot of these other, in some sense, more important questions. All I'm saying is, build the sidewalk so I can walk on it and ask some questions. So I don't know how to reason about some of these things. So that's, I guess, the 2 cents I'd offer. So ask these falsifiable questions and be clear about how you're using the theory and whether you're doing science or engineering.
Jumped right into pub hour, so that's excellent. All right.
Is it on? I guess it's
on.
Yeah,
it is on, yeah.
Yeah, I would like to say, from my perspective, when we talk about scientific foundational models, it seems that we are trying to find a convergence point between two different cultures. And I think one of these cultures is the culture of people who work in artificial intelligence, and the other culture is the culture of the people who have worked in scientific computing. And it's exciting to see this convergence point. In fact, I think between these two areas, or these two cultures, just to paraphrase a very famous statement, that there's plenty of room in the middle. And there's lots of exciting things that can happen there. Now, when we start to see scientific foundational models, it seems that it's in scientific computing we need some help, or something has not worked. So let's take something that has worked in artificial intelligence. And I would like to observe that in artificial intelligence scientific computing, what works or what is considered valuable has been, in my opinion, very different in the two communities. Not only in the way the communities operate, but also in the way and also on the things that the communities value. So if you look at scientific computing, we have been struggling and fighting with each other about validation and verification, and about the flow behind the cylinder, and 10 to the minus 12, and is your convergence really second order as a numerical method, and so on and so forth. We have been very constraining. We have also not been sharing so openly our codes. We actually don't know how to write good code that can be shared. And then you have the other community, that is the artificial intelligence community, that I think has great power by producing software that they openly shared. This actually propagated their algorithms, and this actually, when they went to solve a problem, they didn't care about if the convergence, I mean, Michael said many of these things, but they went and they solved the game of Go. They beat a human in chess, they did protein folding, they did fusion. So the culture there is, do I solve problems, and then I look further in. Now, if you think that AI is the solution, scientific computing should be abandoned, I think that would be a big mistake. Because in the long term, I think it's not data that would help us solve problems. There is a famous statement that how to solve hard problems, just throw massive data at them. Do you know who has said that? It's the founder of OpenAI. But that's not enough, I think. I think there's a lot of thinking that the scientific computing community and other sciences have developed. How do you do science? How do you do scientific discovery? And I think it would be great loss if we abandon all these other things and just focus on multimodal data and more data and throw some machine learning and try to do everything. I think the good way would be to try to find a yin and a yang and try to put these two worlds together. I don't know exactly how, but I think there's exciting ways ahead, and there's lots of young people here that will probably pursue all these things. So I think we live in exciting times.
Yeah, thank you very much. That sets up a very promising discussion, I would say. So I'll first go to the audience, and then I have a few questions here. So who wants to go first? Wow, trigger shy. That's the mic.
Yes, this sort of piggybacks on the comment that was made about neuromorphic computing versus the sort of binary digital computing. I think one argument would be what's limiting performance of AI systems? Is that the training data set, or is it the underlying architecture? But overlaid with that is the idea of power consumption. You're literally talking terawatts versus tens of watts. So I think you cannot really rule out pursuing the neuromorphic, especially in the hardware and the architecture going forward. Just a comment, thank you.
Yeah, I think that's certainly something, and we don't have too many cognitive scientists here, so that would have kind of added more balance. You want to respond? Maybe one response? Yeah. Yeah, switch it on, wait 3 seconds.
It's a great point, but I think that neuromorphic computing isn't even yet at the level of being able to perform complex reasoning, especially when you start talking about those flashes of insight. We don't understand yet, I don't think, in computer science how to capture that with any kind of model, right? Other than some stochastic simulated annealing type of random walk, which is completely inefficient when the space dimension of the hypothesis space is so large that there's no hope that you're going to get there with any high probability. So I agree with you that the neuromorphic computing is a very promising area. It's one that has been, I think, not quite the investment of interest by academia or funding agencies, for that matter, and there should be more attention to that, to finding that common ground that can push us forward in terms of incorporating these types of higher order logics, if you like, into standard machine learning, pattern matching, convolutional networks and foundation models as they exist today.
Thank you. So I have this question which was already beat down a bit as being not that important by some of you, and I do agree with that. But I also want to wear a computer scientist / AI / engineer's hat and ask about, there may be multiple opinions here, the topic of emergence, right? Maybe how it's talked about is maybe not very rigorous, but that is one justification that is posed, right, for using these models. So I want to just pose a question on what definition of emergence are you reasonably comfortable with that exists? And what are your thoughts on, within that definition, the ability of these models to actually provide insight? So maybe I'll start with Heng, because you're a computer scientist.
I'm the most negative one about this question. I think that everyone think that if you keep increasing data, feeding more and more data, you naturally will reach that point of emergence. I think that's a mistake. The reason I'm saying this is because, well, I mean, we don't have to mimic everything human does, right, for machine intelligence, for sure. However, when human is learning knowledge, we do two additional things. One is we can carefully select the data, right, to fitting into our knowledge model, right? You know, we naturally prioritize our time on reading Nature science papers rather than reading, you know, any unpublished abstracts without peer review. And the other thing is, I think we also have a knowledge gate before we decide to update our knowledge or not. So, you know, like, for example, if today someone in the audience told me that women are not good at science, I will clearly remember who said that comment, but I'm not going to register that knowledge into my brain because that violates what I have believed before. And I think the current design, most of these foundation models don't have that mechanism. I mean, yeah, you can rely on probabilities. You know, the learning curve will you know, reach at some point of really high performance, but then you always get stuck somewhere. Yeah.
Any other panelists to respond to it? No pressure. Go ahead.
I mean, I would say, you know, this is probably low-lying. Emergence to me is something that was not obvious in the data, but it could be a salient pattern. But at least the model was not trained directly on that particular aspect, and it shows some of those signatures. I really don't think, you know, we should go beyond that it has shown, you know, emergent ability as such, but likely, you know, there, and I think that's what we are seeing, that, you know, the patterns are not obvious in the data, but it is there, and that's something the model picks up. One thing, you know, in terms of emergence, I'm more excited about, it's a more futuristic view, that emergence happens when many systems learn to work collectively. That's more from a physics or biological perspective, you know, like when a number of systems or agents, each of them may not do something individually on their own, but as they learn together or as they act together, some emergence happen. I'm very excited about, you know, that direction, and I think, you know, that's to some extent untapped territory from the aspect of AI.
Mike, yeah, Mike, and then Al.
So I think as a practical matter, emergence is when the model splits out something that people look at and didn't know they cooked in and are surprised. And it's not quite as simple as I was describing earlier, where you train on 1 to 2 and test on 3 to 4. But, you know, if you train on 500 different tasks, each has vectors in million-dimensional spaces. There's 2 to the million corners in that hypercube, right? So there can be a lot of stuff you cooked and you didn't realize. And then some of it seems sort of remarkable to you, and then you say it's emergence. So in a sense, it's a statement about how ignorant you are, or we are, as opposed to how smart.
An observer issue. I like that.
Yeah. And so I think going beyond that, again, I don't know what emergence means. I mean, I guess the question is, what would you look for in a falsifiable way to make a statement about emergence? Yep. And so an example of that is if you look at, I mean, how do you ask a falsifiable question about these neural networks more generally? So look at models pre-2013, pre-2013. You look at the weight matrices of these models. They're either random or they're random with a few spikes. And I mean this in a very technical sense, Marchenko, Pasteur, et cetera. Post-2013, they all have heavy-tailed eigenvalues. And so you ask, what's the difference between a protein, an engineered heteropolymer, and a random sequence of amino acids? Because a random sequence of amino acids, you heat it up and cool it down, you'll never get the same state in the age of the universe. A protein, you heat it up and cool it down, you'll always get the same state. You know? Why is that? Is there something emergent going on? Is there some complicated stuff put in the million-dimensional hypercube that we don't understand? And so you can look at the protein and use ideas from semi-empirical theory, semi-empirical in the sense that the word was used in nuclear structure theory and quantum chemistry and in fluids, and try and come up with models to parameterize that. And generalizing spin glasses, which have a sort of a simpler structure. People did this in the 90s. It wasn't good enough to get chemical accuracy and predictions, so it was sometimes poo-pooed, but people did this. And this is a paradigm that a lot of physics people have used. Sometimes it goes by a bad name because it's oversold in terms of like complex systems. And so what goes on in there is you get Cook-in heavy-tailed correlations into systems. And so question, could you chew on weight matrices of trained models and make a reasonable prediction? And the answer is yes. And so I didn't have time to go into that, but you can do that. So literally you can predict trends in the quality of state-of-the-art neural networks, BERT and GPT, without access to any training data and testing data. And so I think this is an example of an empirical signature whereby you can ask falsifiable questions that may not quite be emergence, but are the closest falsifiable thing that I've ever seen to what might be emergence. And so you could make a statement like that.
Thank you. That's pretty deep, yeah. Thank you, yeah. Go ahead.
I just want to comment, sort of piling on to what Mike just said, that emergence, I think, is a concept which really is at the eye of the beholder. I believe emergence is a property of the system as opposed to a performance gain that occurs suddenly, that computer scientists tend to use as the definition of an emergence. So, emergence of flocking behaviors among birds, for example. When there's a sufficient number of birds that flock on migratory patterns, there emerge patterns that would not exist if you had just a few in the flock. So just to put a point on that, there was a recent paper at NeurIPS which won a 2023 NeurIPS Best Paper Award by, I think it was a Google group that basically showed what I believe to be the obvious, that anything that you can claim is emergent in terms of the accuracy curve of a machine learning, a deeper learning algorithm, if you make a monotone nonlinear transformation, that becomes a linear curve, and it's no longer emergent, right? So emergence is a property of a nonlinear system that you can't predict, as opposed to a linear system where a linear predictor would be sufficient to extrapolate out to the convergent performance. And this paper basically stated the obvious that any nonlinear monotonic function that has a knee in it that appears to indicate emergent behavior can be normalized by using a different metric on the error to turn it into a linear function, and then it's no longer emergent. So it's sand between the fingers. There's really no, I think, no currently rational definition of emergence for this type of phenomenon.
All right, Petros?
I'd like to borrow a little bit from AI and say that emergence is a relationship between a system and an observer. It's not something that we all share because we are all different observers. Obviously, we all understand the flocks of birds, but it's a word that is very subjective, and I think this concept of emergence, at least as it pertains to scientific foundational models, will become a little bit more useful if we are able to quantify it with metrics that are agreeable across the board. Otherwise, all these concepts of emergence, homogenization, etc., are fancy words. Sometimes they're just reinventing the wheel. We had emergence in scientific computing forever. I write you down the Navier-Stokes equations, and then you get billions of wonderful things happening, and that's emergence somehow. But it's something that needs to be quantified first of all, and then we can talk about it perhaps in more intelligent ways. At least I don't have more than that to say on that.
I doubt anyone really has. All right, question to the audience. Yep. Oh, sorry.
I want to put a hypothetical case about emergence again. Imagine.
Can we not do emergence because we only have
okay.
16 minutes.
It's not about emergence, but no. Imagine a time when most of the discoveries were not made. Kepler, Gauss, Newton, and all of them. but they had good observational machines and data. Would AI or science, the SciML as exists today, would it have helped them make their discoveries faster?
I can take that. I mean, you put a prior there, which is quite unrealistic. You give all of a sudden, in the time of Kepler, huge computers and huge data, and then it was time of Kepler, people were killing each other and dying at the age of 30. So I don't know if this is possible to answer at all. I mean, because there is something in science that we forget, and actually machine learning people in particular forget it, and they don't know how to deal with it. This is time. Time is an unknown territory for machine learning. They do patterns, they do images, they do these things. Time they cannot do very well. So the time in which you pose the question, in your particular question, is extremely important, because you cannot take things from the future, plug them in the back, and say, oh, would Kepler be able to do that? God knows what Kepler would be able to do, but the thing which is amazing about Kepler and other people, and humans in particular, is that we are able to devise things that did not exist before. And that I think, if we are able to understand how we come up with that, I think there will be a lot of hope for automating it and doing artificial intelligence. I think this relationship of natural and artificial intelligence is very, very powerful. I hope I did some justice to your very nice question.
So, can I add something? I think it's a wonderful question which I've asked astronomers too. And if you look at Kepler himself, I mean, he spent decades basically trying to fit all sorts of different equations to the data he had. So it was a very mechanical process, which I think could easily be automated. On the other hand, if you look at, say, Newton or Einstein, you know, they were looking for explanatory laws rather than just curve-fitting equations. And so there we need a mechanism for generating hypotheses that are perhaps not apparent in the data. So that's much harder to do, I think.
So, I'll attribute this to Al, because he said, but, you know, if Kepler had least squares, the answer might be different. And with these language models, that may be cooked in a language model. So we don't know whether you're conditioning that he knew that or not. A related question I've wondered about is, so Kepler, to gloss over the Kepler versus Newton and the historical contingencies, I mean, a lot of intuition people have comes from one dimension related to the time question. And so it's either asymmetric like time or symmetric. But, you know, there's a book, Statistical Mechanics in One Dimension, where every problem has an analytic solution. And if you go to statistical mechanics in 2 dimension, there's one problem that has an analytic solution, nothing else. In 3 dimensions, nothing, right? So 1 dimension is incredibly, 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 and if I had more time, I'd say more incredibly special compared to any other metric space. And so say that you had this and Newton or someone that wanted to understand how things move and notion of continuity. What if, rather than starting in 1 dimension and then going to 2 and 3 and a million and thinking that a million looks like 1 or 2, you came the other way and you said, go from infinite dimensions back on down. And that's not a hypothetical thing, because, you know, if you think just pedagogically, you explain to students, you know, there's Chernoff bounds and Chebyshev and so on in 1 dimension, and then you just hold your nose and hope that matrices are all the same. You know, and you say, no, what if you came from the high dimensional perspective and cut back? And it's not unreasonable. This is what you do in statistical mechanics. This is what you do when you anneal a temperature. So what would they have done? And technically this, you know, are you in an asymptotic limit or not? Do your 2 parameters diverge in the same way or not? And so the way high dimensions behaves is very strange. So I think a question could be is if Kepler knew infinite dimensions as well as he knew 1, what would he do differently? Because a lot of the information that's cooked into these models implicitly has a strong bias towards that in ways that aren't fully understood.
Right. Other audience questions? Yeah. Go ahead.
Okay, 1, 2, 3. Okay, we're live. You said before it would be good if there was some cognitive scientists here. Well, there's at least one. So all we've seen thus far are transformer models, right? On the other hand, if you have a look at scientific practice, there's a lot of non-standard reasoning ongoing. There is analogy. There is serendipity, as pointed out before. And I think, Heng, Alfred, you already went in that direction. What would you think comes after transformers? So what would you think do you have to add to them? What do you have to do foundationally differently in order to actually push more towards getting away from really smart calculators, getting into a territory where you do have novelty, where you do have hypothesis generation in the proper sense? Like, where are we on the architecture there?
I'll just add one small thing there. Also, compositionality properties are very poor with transformers, and that is what we need for reasoning. So just adding to that, but thank you.
Actually, I need 500 GPUs, and then I can deliver that by the end of this year. So we already have a prototype. We are doing this for the kinase inhibitor problem that I mentioned yesterday. I'm not able to scale this up even for chemistry domain because I don't have computing resources. We do have ideas. We have data. We know what data to use. We know how to make every step, the better reading mechanism, reasoning, like a multi-agent debate. We have all of those design ready. I just cannot do it without the computing resources. So either anyone from bigger companies donate your resources, or maybe we work together as a
that's the second panel topic.
Share the infrastructure. Yeah. But thank you for pushing on that direction, though.
So your first question will go to the second panel, but I want someone to respond more directly to that question.
So I'm not quite sure what transformers are actually doing in a sense. If you look at what they did, I think there's a notion of recurrence, which gets to the time question. And in a sense, they do recurrent type models just faster via black box mechanism that you could understand or not. And so if you black box the computational time, which scale model data compute says maybe you shouldn't even be saying this, but if you black box that, in a sense, they're a way to do some sort of parallel computing on this recurrent structure, and it's the recurrent structure that you see in NLP. This didn't come from CV. I mean, maybe it went back, but so if you think of that as time as a first class, and you want to get some sort of recurrent structure, and now just do it fast, I could imagine where I want to get a 2D or 3D geometry, something fancy than vision transformers, and cook that in a right way. I could imagine you want to cook in some other sort of structure that allows you to do formal reasoning or something at a micro level, and then figure out a way to parallelize that fast. Because you're going to need to be fast and parallel and press that big button, whether it's on the hardware or from the ML perspective. So I don't know, but a lot of the stuff that I hear about sort of formal reasoning is, I could imagine that gets cooked into some capsule that then you transformerize. Yeah.
Let me add to that, because I think, indeed, the recurrence is a critical component, but another component which I think is as critical, if not more so, is attention. And with language, speech, any other one-dimensional living symbolic sequence, attention is difficult, but it's not impossible. If you go to large dimensions, or even infinite dimensions, it scales geometrically in terms of the number of masking configurations that you would have to consider for attention in even 3 dimensions is 3 orders of magnitude more than in 1 dimension, well, 2 orders of magnitude. So I think that what would be needed perhaps would be another form of attention where you could parameterize the space, for example, if it is mathematical reasoning, in some sort of lower dimensional subspace, a manifold, not necessarily smooth, where you could traverse that space as easily as in a low dimension, as opposed to in the extrinsically very high dimension of any logical clause, which consists of more than 2 or 3 different logical statements.
I just want to clarify, maybe my comments already was a little bit misleading. I'm not suggesting we abandon transformer. I think transformer is a genius idea. I'm proposing to do some extension or enhancement on that framework, that self-learning idea, right? So the attention is also about word association. So basically you have a current word, you look at all the other related words in the context. But it's not exactly knowledge association. If we look at a word indicating a molecular entity, when we read that word, we immediately connect that with the, like the properties in knowledge base, right? Like the weights and the mass. Those are not written in the content sentences, or maybe the corresponding related gene sequences. So I'm just saying, we need to go beyond just reading the neighboring sentences or neighboring words. So you should not expect that we throw in more and more papers. This will naturally happen. We need to better design to teach this model to become smarter and more efficiently.
Yeah, so Vaswani 2017 is not the frozen idea, right? So there is a lot more enhancements. From a practical perspective, I certainly agree. But I think from the cognitive science perspective, I don't think he got a good answer, but feel free to harass them over lunch, sit in their table, and you can pursue these questions more. You have a question? Any other questions from the audience? Okay. It's on.
This discussion is like very, very interesting. So we often talk about attention is all we need, but I think like what I'm hearing is we want these models to be learning through observation also. I mean, because I heard like people talk about like how the previous like discoverers, they observe things and then they try to figure out what's the answer. When we talk about sentence reading, like the professor Hengji said, that they're talking about, okay, this is an important word in the sentence, and that prompts them to predict what the next word is. But thinking about what's happening around the world, what's happening around the environment. So I think like things, if they could be extensions for 3D models, that could be one. There's a lot of space. There's a lot of, I think, advancement in the robotic space that can help take these like foundation models to the next level. I mean, I would want to hear like what does the panel think about this?
Okay. Yeah, I think it kind of revolves around what Heng was getting at, which is building things on top of attention, and also what Petros and Mike also spoke about. So any quick responses to that? Yeah.
I'd like to share a personal experience here that I'll try to connect to your question. About 20 years ago, I was in Japan. I was doing my sabbatical, and I had the opportunity to attend a conference where they had collected about 20 Nobel Prize winners, and these Nobel Prize winners were sharing their wisdom. And I recall very vividly, it was a Nobel Prize winner in physics, and then they asked him why people in Japan, at least, don't have more Nobel Prizes in physics. And he said that when people were younger, they will be out in nature, and they will touch the trees, and they look at the plants, and break stones, and then slowly you start to understand the physical world, and you get interested in the physical world, and then you start to think about physics. So the way I would like to connect it to the statement that you made about observations is that when we slowly start to go into all this machine learning virtual world of ChatGPT, fake images, and so on and so forth, I have young kids, and I'm worried that the things they observe and the things they see have nothing to do that is sustainable and can last for long in the future. It may be good for now to make a quick buck or whatever, but I'm worried about these ways of thinking that seem to disappear. So that's my pessimistic comment or warning comment to your point.
Yeah, so last week, the Weinberg Institute for Cognitive Science organized a very wonderful, very nice symposium on natural versus human, natural versus artificial intelligence. And they kind of touched upon this, how we learn principles in real life and how the computer learns it. All right, so we're almost at time. So I want to do some kind of a rapid fire round. So I'll basically prompt each of you. And Petros, I'll go with you first this time.
I talked enough.
No, but it's a more general question. And at least in my opinion, I mean, first of all, I want to wear two hats, right? On the one hand, I see the progress over the past year as incredible. Even what was shown yesterday here and today, how much has happened in the past year and how much mileage we've gotten out of these models, staying within the current infrastructure, current framework, current transformers, etc. Right? So all that is great. And I think that over the next 2 years, there is a lot of low-hanging fruit that we can pick. And I don't think there'll be a lot of questions asked. Well, maybe not, we won't get as much money as we want, but other than that, I think there'll be support. And I feel very soon there is going to be a cliff that's coming when people say, so what, right? So what have you accomplished? So I want each of you to speak about anything related to what I said, and particularly, even beyond Hello World, what is it that, just address 2 things, right? What is it that you've seen that is impressive in your mind? And what is it that we should do, or we should try to do, to keep this field going, right? So when the loan sharks come back and ask tough questions, right? So I know it's a little ill-posed, but in the spirit of, again, just rephrasing it, what is the most impressive thing you've seen roughly in this field? And what should we be doing in the next few years to actually show value? Or what should we be trying? So Petros first, and then...
I think it's an amazing new dimension, these large language models, and I think it deserves a lot of exploration. I think predictions about the future are tough, as we all know, but I think it's 2 ways so that one perhaps can approach it to be sustainable. Ask hard and honest questions and be ready to be acknowledging failures, because that's the only way that we will progress. If we get stuck in some hype, we will not progress. But if we are honest that about this thing fails or this thing succeeds, I think we can proceed. If there is a cliff, I'm not so sure, but I think it's a very interesting area.
There'll be a cliff in some problems, but I'm 100% convinced that in some of these domains, they're going to completely transform the field. I have no doubt. But in kind of the fields that I work, I feel there may be a cliff. And where you work, I feel there'll be a cliff.
In some fields, I think there will be a cliff, yeah. Mm-hmm.
All right, so thank you. Mike?
Yeah, so I think ML has a long history of sort of maybe weathering, but also maybe encouraging hype cycles. And so, so the question's not, when, if, but when. So there'll be a cliff, and I think be honest about what you're doing and ask a real question and keep your eye on a real target. So the cliff part of ML, it's driven by the fact that industry drives it, not just in the sense of the last few years, but they're a forcing function and scientists are not. And so scientists tend to have sort of a longer view, for better and for worse. And so I think focusing on where there's been sort of real successes and why there's been the successes. So the AlphaFold is an interesting example, because one of the early successes was in an area of science that played very well with the ML form factor. There's a leaderboard. I mean, I think someone made a comment yesterday, says we don't really understand, or maybe it was that, why protein structure works. It just works because, but there's a black box model that says it works. I mean, if any domain scientist had gotten a spike with their model, and the model could be whatever story you want to tell, they'd be jumping around and dancing, saying, see, my story and my theory is right. So the fact that now you have a model that's a black box that isn't doing that, it's understanding at least as much as the domain scientist would. So the AlphaFold played well with the ML form factor, because it's just a leaderboard of numbers. If you do better on that numbers, you are the winner. And then we ask later, how did you do it? And, oh, you did it because this black box thing you can't explain. I mean, so it played very well with that. It also played well because you have a lot of simulation you could train to. So one of the downsides of the PDE approach I was describing earlier is you could only get as far as the PDEs will go. So you could train to PDEs, you could do a range of things, but that's current simulations. It's what you can do already. So don't compete with that. Compete with something you can't compete with, namely actually folding the protein, because you couldn't fold the protein by running computer factor of 1 million longers. So learn things here, take training data here and learn something that scientists can't learn. In that case, it was a bunch of free energies and variables that you get with coarse grain, and use that to make an inference on scales you couldn't, namely what does the actual folded protein look like. So if you just want to do this stuff for better simulations, you'll lose because the HPC people beat you up. And even if you find a place where you win, they'll beat you up because they don't understand, right? So focus on a problem, a real problem that they have that fits well within the form factor of what ML does, and you'll be able to weather the storm that way.
Good advice to all the PhD students. If it's too late, I'm sorry. But Al?
Yeah, I think it's a very, very difficult question that you asked there, Kartik, because it's hard to rank all of the methods that I've been, really impressed by that have come out in the past 2 or 3 years. But one thing that I don't think that has been as much addressed at this meeting, but which I am very, very impressed by, is this concept of marrying dynamical systems, reinforcement learning in particular, with large language models, where if you look at AlphaGo, for example, the key or the trick behind it, look beyond the hardware and the data and so forth, was self-play, right? So basically, running millions, hundreds of millions of simulations under different assumptions in silico that then learning from each one of the outcomes as to what the next strategy should be. This kind of approach, I think, is extremely promising and has just, I think, begun to be yoked with foundation models, and I find that very, very intriguing. I also think there's a note of caution, and that is I do indeed think there is a looming cliff. I am hoping that cliff won't be widespread, but I think the main component in determining whether that cliff is near or far is trust. And if there is not so much hype and let me say, expectation building in the CS, scientific, or other communities that, as has been said before, we are more, let me say, moored in our hypothesis-driven training as scientists and engineers, and look to, incremental progress and applaud when a leap is made, right? As opposed to the opposite, where we try to get a leap and things turn out to be incremental and people then are effectively disappointed. And if that happens on a large scale, there will be I think a severe loss in trust on these types of machine learning approaches to science that will, I think, be well-founded, a loss of trust.
Thank you very much. Hank?
I want to echo what Kartik said in the morning about opportunities and risks moving forward. When I was an undergrad student, NLP, anything related to language modeling, is the least popular area in CS. No one wants to do it. And now it's almost feel like it's the center of CS. Like half of my colleagues in my department are doing something related to LM. So I think the LM people, us, often pretend that everything's done. We found the solution. It's a solved problem. You guys just adopt it, right? So earlier, you have some nice comments about whether we can inspire from the robotics research to help us enhance the current method. But unfortunately, that's not what's happening now. What's happening now is the opposite. So we always, claim that this is a very powerful tool. Other people should just use it, right? So I think we should change the attitude. Try to be more humble again. Let science guide us in addition to the other way around. Because every language in every domain is different, right? So are we really done with our design of the architecture or how we do pre-training, how we do fine-tuning, right? So I think now the community is so much bigger, right, than before. We should shoot for higher goals, more ambitious, instead of just doing similar things incrementally. And then the other thing is that I'm super unhappy that most of us pretend that the success of OpenAI is the success of AI area or the LLM community. Honestly, looking at the gap, right, performance gap between all of the open source large language model and what OpenAI GPT models can do, it's really depressing. So if we don't catch up, if we don't do anything more innovative or better, we will be falling behind. We are already falling behind. And they are never going to share their model. So we urgently need a academic-owned, completely open source, much more powerful framework. And then we build on top of it, keep improving it.
Right, you set up two of the first questions for the next panel, but you're a unique computer scientist, I'll say that. All right, Payal.
I think, when you are sitting on this side of the table, a lot of things are already being told. So I would echo some of, I think learning is what we see is prevailing right now in the AI field. I think learning plus search, that's something we should look forward. Learning to construct a world model by self-playing, self-reflection sort of techniques, and then constructing a memory of such moves, and then learning to search in that space. That's, from the algorithmic side, is something that's going to change how we do things today. In terms of ability of current models, one thing that often bothers me is that it seems like we have forgotten how to evaluate models in a more standardized way. We're told that, that we should always benchmark a model in a held-out data set, and now you go and check that some of the models are doing so well because the test data is already being fed to the model. So I think, that we need to, as a community, we also need to think about what are some of the toughest challenges that are meaningful rather than some benchmarks that's sitting somewhere or that has been contaminated already. That what are some of the meaningful challenges that we as a community should think that, not thinking that the answer already is one of the language model or one of the large model today, that what some of the models cannot do today, and I already had thoughts that, robotics is something that we should learn, get inspiration from, and, come up with a model that would be built to solve a particular big challenge, something that is needed, not just to be competitive, but because there is a significant gap in terms of capabilities today.
Thank you. Ian?
So Michael mentioned AlphaFold as being a perfectly aligned problem for machine learning. But one other aspect of it is just there was the vast amount of data that was available. Much of it actually produced at DOE labs, representing certainly hundreds of millions, probably billions of dollars worth of investment. So, and of course, natural language processing is another domain in which we've benefited from vast amounts of human-generated data. So we need to be looking for areas where more data is available rather than trying to process the current data even more than we are. And also, so then that leads me to the question of where am I excited? I think areas in which we can generate data, have our large language models generate data automatically, either by interacting with the world, either by controlling robotic laboratories, running simulations, generating software. I mean, there's some wonderful work going on with people learning how to encode protocols and software and then try the protocols and improve them, self-learn in worlds in which perhaps we didn't think self-learning was possible.
And I would recommend staying for Ian's talk, which is going to be spectacular on pretty much the things that he spoke about. High bar. Right.
I agree with much, if not everything, that the panel has said. I think we are in a bit of a hype cycle, clearly, and the field is being primarily driven by commercial interests, and we don't have a lot of control. I also think that there's a lot of room in the middle comment. It would be really a shame if we reach a cliff and that disrupts, I think, this fascinating collaboration which is happening. I think there are a lot of near-term gains. During the breakfast, I was talking to a couple of people from MIT who are working with some collaborators at the lab on looking at extracting synthesis recipes from really old chemical journals and more recent journals, and these articles are structured more like spells than modern scientific papers. And I think that shows a lot of promise, being able to really get to synthesizability of new materials.
Thank you very much. This was a spectacular panel. Thank you so much for all the insight, and thank you for the participation.